Here's the second example for functions defined as integrals. It says let f be the function whose domain is the closed interval from 0 to 5. The graph of f is shown below. So here is f of x once again, and there is our domain of f. H of x this time is defined to be the area accumulating in the plane from 0 up to 1/2 x plus 3 between the function f and its horizontal axis. Part A says find the domain of h. Well, there is a relationship between the domain of f and the domain of h, and that relationship has to go through this upper limit. Before, on the last example, we accumulated from 1 up to x, and the domain of f was from 1 to 7. And the domain of f and the domain of h had a 1-to-1 relationship. X was the 1-to-1 relationship. Now here, we don't have that 1-to-1 relationship between inputs of f and inputs of h. Here are how inputs of h are defined. So let's come up here and let's do this work for part A, and we'll see how we find the domain of h. So the domain of h of x will lie between the endpoints on f, and specifically as far as x is concerned, we'll have this relationship. Now we just need to solve for x in between our endpoints, and then we'll have the domain of h. So I'm going to subtract 3 from all three pieces of this inequality. So -3 is less than 1/2 x, which is less than 2. And I'm going to multiply all three parts of this inequality by 2. So -6 is less than x, which is less than 4. So -6 and +4 are the endpoints for the domain of h. And there's how we would answer part A. Here's part B, find h prime of 2. So let's write the definition for h down again so we have it here where we can look at it. That was 1/2 x plus 3 f of t dt. And again, we're looking at the graph of f of x. That might help us answer these questions. The process that I showed you on the last example is please show the AP reader h prime of x first. Then you can show the AP reader where you substituted in x equal 2. So h prime of x is the derivative with respect to x of what h of x is defined as. So that's 0 up to 1/2 x plus 3 of f of t dt. Here's where they're testing, do you understand the chain rule in the fundamental theorem part 2? The chain rule says it is the derivative of the outside. We write this function. Everywhere there's a t, we replace it with whatever is written in the upper limit. That's the derivative of the outside, not changing the inside, times the derivative of what's inside with respect to x is 1/2. So h prime of x cleans up to be 1/2 times f of 1/2 x plus 3. And so that's how we're going to find h prime of 2. That has to be 1/2 of f times 1/2 times 2. I'm substituting in x equal 2 plus 3. So that's 1/2 f of 1/2 times 2 is 1. 1 plus 3 is 4. So it's 1/2 times the output of the function f at an input of 4, and that is -3. So this is -3/2. All right, so if this was a 1-to-1 relationship and the upper limit was just x, then h prime would have been f of 2, which would have been 0. And so that's probably what some students would answer if they don't understand the chain rule part of fundamental theorem part 2. All right, and finally part C, at what x is h of x a minimum? Show the analysis that leads to your conclusion. Well, the first thing that we're going to look for is we're going to look for our relative mins. We will have a relative min. We would say h of x has relative mins where h prime of x changes from negative to positive. So let's go look at our graph. Are there any x values here where this graph changes from negative to positive? And we can clearly see there's not. Now there's one x value here where it changes from positive to negative, but not negative to positive. So the only candidates are going to be the endpoints. The endpoints on h, not on f, the endpoints on h of x are the only candidates or only critical points where the absolute or global, which is what it's asking for here, where is it a minimum, absolute or global minimum can occur. So all we have to do is show h evaluated at the left endpoint and h evaluated at the right endpoint, and whichever one of those is the lowest output value is the absolute or global min. Now, the problem here is most students would put 0 in here and 5 in here, but those aren't the endpoints on h. The domain of h is -6 to 4. So we need h of -6 and we need h of 4. So again, we're going to show the AP reader. We understand that's accumulating the area in the plane from 1/2 times -6. I'm substituting in -6 for x of f of t dt. So this is actually area accumulating between 0, 1/2 of -6 is -3, plus 3 is 0. So I'm accumulating area from 0 up to 0. So that's that property where I start and stop at the same input value, so that accumulates to 0. Now I'm going to compare that with what the output on the function h is at x equals 4. So I'm going to substitute in 4 for x. So that is actually accumulating area. 1/2 of 4 is 2, 2 plus 3 is 5. So it's accumulating the area over the whole domain of f. So let's try to do that. We have +1, roughly we could call this area and this area maybe +2, and that's, I don't know, we would call that maybe 1/2. So 2.5, we would call that 5/2, that's positive. Then we're going to subtract all this negative area. We'll call this and this -1, 2, 3, 4, 5, and we could call that another 1.5. So 6.5, we'd call that 13/2. So that's roughly about -4. So clearly we can see from this work where we plugged in our endpoints on h that the minimum for h of x is at x equal 4. All right, so when that upper limit is anything other than x, we've got to keep that in account on all of these finding the derivative or finding, evaluating endpoints for global or absolute maxes or mins. All of that's going to make a difference. So we'll practice some problems like this when we come to class next time, because again, I really feel certain that you're going to see a free response question that is a function defined as an integral.